So this lecture is the part 1 of our discussion on regression analysis. So we will start our discussion on linear regression with an example. So here we collected information on 25 rental properties shown in this scatter plot. So each point represents a rental property. The y-axis represents the rent information measured in dollars, and the x-axis represents the size of the property. So for example, for this particular property, its size is about 3,400 square feet, and its rent is $2,000 per month. So we are interested to see whether we could predict rent of each property based on its size. And we call the variable we are interested to predict as a dependent variable, and conventionally denoted as y. And we call the variable size here as an independent variable, conventionally denoted as x. And the reason we call them this way is we are making an implicit assumption that how much does a rental property cost is dependent on its size. So by visualization, we can spot a few trends in this scatter plot. An obvious one is, as size increases, the rent increases too. Another one is all these 25 properties, each represented by a point, seem to clustered around a line that goes through from the lower left corner to the upper right corner diagonally. So linear regression is to find such a line that can best capture the trend exhibited in data similar to this rent data set. So we know that a line can be written algebraically this way and defined by two parameters. So the B0 is what is known as the intercept, and B1 is what is known as the slope. So to find such a line that can best capture the trend exhibited in this scatter plot is to find the two values that come to define this line. So we'll next look at how this can be done with the help of Excel. So the raw data is stored in this data tab, and to run the regression analysis, you need to find the data tab on the menu and then go to and find data analysis. Of course, you need to make sure you have installed the data analysis toolpad as an add-in product for Excel. So you click data analysis, and you should be able to find regression as one of the tools, and click on OK. Now you need to specify what is the dependent variable denoted as y. So here our dependent variable is rent, and then you need to specify what is the independent variable. In this case, it's the size measured in square feet. So once you have done that, click labels to indicate the headers is included in the range. Click on confidence interval. Make sure you click this option, new worksheet apply, and also click line fit plots, and then you click on OK. So the result is produced in a separate tab, and this number is the intercept B0, and this number is the slope B1. So based on the Excel regression analysis output, we know that this line identified by the Excel regression analysis has the intercept of negative 483, and it has the slope equal to 0.6784. So once we identify this line, we can plot this line represented by this line along with the original observations represented by the blue dots. So what is such a regression line good for? There are two main purposes of applying linear regressions. The number one is for prediction. For example, given this regression line, we can plug in size equal to 3000, and based on this linear functional relationship, we can calculate the associated rent should be around 1551. And notice that the size of 3000 square feet, somewhere around here, is not included in the original data set. So that is the first application of linear regression for prediction purpose. A second common application of linear regression is to understand the relationship between the two variables in question. By interpreting the coefficients in a functional relationship, for example, knowing slope is 0.6784, one of possible interpretation for B1 equal to that value is, for each additional square feet, it demands additional $0.6784 in rent. So in this lecture, we'll discuss three things. In section 2, we'll discuss how these two values, namely the intercept and the slope, are found by linear regression through Excel in section 2. So in section 3, we will evaluate how accurate or how reliable such kind of prediction we just show. And in section 4, we'll assess statistically how valid our interpretation on B1 is through hypothesis testing. So we'll next look at how to find the line that best captures the trend. Use the so-called least square methods. So it seems sensible that the best line should be the one that provides the best prediction, i.e., the least amount of total prediction errors. We'll now look at this graph to see how we can define the total prediction errors. So this is the regression line, and given a point in the data set, in this case, this is the point associated with 3,300 square feet, which is rented for $1985. Given this point, we can calculate a predictive value of rent based on this regression formula. So if you plug in 3,300 into this equation, it will come up 1755. So it seems natural to define the error to be the difference between the predicted value y, and this notation is pronounced as y hat. So the y hat minus y, which is the actual rent. So if we define error this way, then the error will be negative 230. So it's underestimation of the rent based on the regression line. So similarly, we can look at another point. Here again, the blue dot is the actual observation in the data set, which is associated with 2,800 square feet and 1369 in rent. So our regression, based on the prediction of our regression line, the same square feet will be associated with 1416 in rent. And similarly, by the same definition of error, you will come up with 47. But this time is a positive value, meaning you are actually overestimating the rent. So in order to calculate the total prediction errors, we need to somehow aggregate each error associated with each point. But realize we cannot simply sum up error like this, because this one is positive, this one is negative. So they will cancel out each other and give the false impression that the errors are small. So one solution to this problem is we would square each of the individual error like this. So we'll square 47 to come up with 2209. We'll square the negative 230 and to come up with the 52,900. And then we can add up all the errors associated with all the observations in the data set. And that is the definition of sum square errors, also known as the error sum of squares. And so mathematically is defined with this formula. Notice this sum of square formula is defined for any line, meaning if you have a line that goes like this, it will be associated with a different intercept and a different slope. But you can still also apply this equation, this formula, to calculate what is the sum square of error associated with a line that goes this way. So by choosing different values of intercept and slope, you would have different orientation of the line. So some of them might provide a greater sum of square errors. Some of them might provide a smaller sum of square errors. So our goal is to find a line that provides the least amount of sum of square errors by seeking the proper value for B0 and B1, namely the intercept and the slope. This should remind you of the problem of optimization. So if we use the language of optimization, then B0 and B1, namely the intercept and slope, will be the two decision variables. So we try to find the best combination of the two values so that their associated line can minimize the sum square of error. And also, in this particular case, we do not have any constraints. So let's now do a quick comparison between linear programming and the problem we have, and to see how they differ from each other. So in this graph on the left hand side, I add one more axis to represent the value of objective function in linear programming. So once we identify the feasible region in this two-dimensional decision variable space, we can calculate for each point in this feasible region, we can calculate an associated value for the objective function. So if you do so for every point in the feasible region, the resulting values of the objective function would actually look something like this. Imagine a slice of pizza floating in the mid-air. So if your goal is to minimize this expression, then you realize the minimum point will be here. But if you project the minimum objective function value represented by this point down to the two-dimensional decision variable space, you will then find out which of the corner is the optimal solution. So this is the three-dimensional representation of linear programming with constraints. You have three constraints here that jointly determine a feasible region. Let's now look at the graph on the right-hand side. So in order to find out what is the best value of intercept and slope, we need to apply something called quadratic programming. So if you simplify the sum of square error expressed this way, you would end up with something like this one. So it's called a quadratic expression, which is the sum product of b0 squared, b0, b1 squared, and b1 with some constants. So this expression is the sum of square errors. So our goal is to minimize this expression by finding the best value of b0 and b1. And similarly, the b0 and b1 are the decision variables. The same way to a problem in linear programming. So in this case, any point in this space is a set of values that are associated with b0 and b1. So each point in this two-dimensional space representing a different line in this graph. So our goal is to find what is the best b0 and b1 so that we can minimize the sum of square error. And as it turned out, this quadratic function looks like a half football floating in the air. Therefore, even without any constraints in this case, we can still find the minimum value for this objective function, which is represented here. So by projecting that value down to the decision variable space, you can also find the optimal solutions, which are the particular values of b0, the intercept, and the particular value of slope b1 that would provide a line that results in the smallest sum of square errors. So the solution or the formula for b0 and b1 from this optimization problem is given in the textbook. And of course, the formula is how Excel calculate the regression equation as we had just showed earlier. We'll now look at, once we find the minimum sum square error and the associated regression line, how good is the overall prediction of rent based on the size of a property. So this is done by what is called measures of variation, namely identifying different sources of variation. we need to first establish a baseline prediction, which is if we have no knowledge of the size of the property, we only know the rent. If we were to make a prediction of a new property, what is our baseline prediction? And in fact, the best prediction we can come up with without a knowledge of the size is to calculate a simple average of the rents based on the 25 properties of which we had the rent information. So in this case, the average comes up to be $1,135. So since we do not have the size information of each property, given a new property, the best guess we can have, or the best prediction we could have, is simply $1,135. So if we refer to this graph, since we do not have the x-axis information, so for any property, our prediction is the same, which is represented by the y-bar. Again, y-bar is calculated based on the average of the 25 properties. So let's take this property as an example. So without the knowledge of the size of the rental property, the best prediction we can come up with is the y-bar represented by the average of all 25 properties. And so the error by this prediction for this baseline situation is represented by this segment. But once we have the knowledge of the size of the property, and with the help of this regression line, we can plug in the size equal to 3,300 square feet in this regression line, and the resulting prediction becomes 1755, represented by y hat. And then the error of this prediction becomes represented by this segment. And you can see the error based on the regression line is significantly smaller than the error associated with the baseline prediction. So you can apply the same logic on each of the remaining 24 properties to calculate the baseline errors versus the predicted errors with the regression line. So if we sum up all the baseline errors square over all the 25 points defined here, then we'll arrive at the concept of total sum of squares, represented by SST. And then intuitively we know that a more predictive regression line should produce a smaller sum of square error in relation to the total sum of squares. So if we define sum of square of regression as the difference, the two, then we can define a ratio which is represented by R squared as sum of square associated with regression divided by total sum of square. So the higher the value of R square, the more predictive the regression line is. And it's also known as coefficient of determination. So due to the geometric property of these three variations, R squared is always going to be greater than 0 and smaller than 1. And again, as I said earlier, the higher the R-square, the more predictive the regression line is. And let's go back to the Excel output. This value is R-square. So this is the result provided by the Excel regression analysis functionality. So we'll now move on to the last topic of this lecture, which is linear regression model. And a simple linear regression model is represented in this box, which looks like this one. Y sub I equal to beta 0 plus beta sub 1 times xi plus epsilon I. We will first contrast this model with the regression equation or the prediction line we have discussed so far. So superficially, you notice that the y hat is replaced by y, the b0 and b1 are replaced by beta 0 and beta 1. And in the equation line, the term epsilon, it was not there. So these differences are caused by the fundamental difference between a linear regression model and a regression equation, which is, in a linear regression model, there are a set of assumptions associated with the model, whereas for a regression equation, there are no assumptions. So it's simply a line that we found by applying least square methods. So we'll now look at what are the assumptions associated with linear regression model makes it different from a regression equation. So the two major assumptions associated with linear regression models are, the first one is the dependent variable y is related or determined by the independent variable x by a linear function with some unknown beta 0, which is the intercept, and beta 1, which is the slope. The second assumption is the actual observation of y values are contaminated by random error denoted as epsilon, which itself is a random variable that follows a normal distribution with mean equal to 0 and with the unknown standard deviation. So the random error term is also referred to as the residuals. Now we will interpret these two assumptions using the example of the rental property. So the first assumption states that there exists a perfect linear relationship between rent, which is the dependent variable, with the size, which is the independent variable. However, we do not yet know what the true intercept and slope of the line are. So if this assumption were to be true, then we should expect each of these blue points, each representing a property, should all line up in a perfect straight line. And as you can see, this is not the case in this example. And this is explained by the second assumption. Our second assumption says for every actual y observation, they are contaminated by a random error terms, which makes each of these points deviate from this underlying line that we do not yet know. So once you know the meaning of the two assumptions associated with linear regression model, then to build a regression model is to estimate these unknown parameters with limited observations. So we do so by using B0 and B1 from the least square methods to estimate the unknown beta 0 and beta 1 respectively. In the same way that we use the sample mean to estimate the unknown population mean. Also, in the same sense that we know that the more observation we have, the more accurate our estimation of B0 and B1 to beta 0 and beta 1 will become. And also, similar to using the sample standard deviation to estimate the population standard deviation, we can use the sum of square errors from this regression line to estimate the underlying random error term represented as epsilon by using this formula. And also, in the same way that we conduct hypothesis on the population mean using the sample mean, we can conduct the hypothesis on beta 1, which is the slope, using B1 as the test statistic. And there's a particular hypothesis that's of great interest to us, which is written as this. So the H null states beta 1, again the slope equal to 0. The alternative hypothesis says beta 1 is not equal to 0. And the reason this hypothesis is of great significance to us is if beta 1 is equal to 0, it implies that the regression model will be reduced to this one, y equal to beta 0 plus the error term. So this implies that there is not a linear regression, there is not a linear function, no relationship between y and x. So in other words, y and x are independent of each other. Therefore, we cannot predict y based on x.